The second phase of the Quine-McCluskey method focuses on finding the optimal cover for the function based on the list of prime implicants generated during the previous prime implicant generation phase. This phase operates on a table known as the prime implicant chart. In this table, each row represents one of the prime implicants identified during the previous prime implicant generation phase, and each column corresponds to a minterm of the function. Note that don't care terms are excluded from the columns, as they do not correspond to function outputs equal to 1. The prime implicant chart is a binary matrix in which each cell contains either a 1 or more simply an X, if the prime implicant in that row covers the minterm in corresponding column. If it does not cover the minterm, the cell is left blank or filled with 0. Let's consider the following example of function. We begin with a list of prime implicants that have been generated through the prime implicant generation phase. We leave the actual derivation of those implicants as an exercise. We now construct the prime implicant chart as just described. For instance, P0 covers 0, 1, 8, and 9. However, since 9 is a don't care, we only place X marks in the columns corresponding to 0, 1, and 8, while we don't have any column labeled with 9, and so on for the remaining prime implicants. Note that there is at least one X in every column, because each minterm must be covered by at least one prime implicant. There is also at least one X in every row, because each prime implicant must cover at least one minterm. If either of these conditions is not met, it indicates an error, either in the calculations from the expansion phase or because we mistakenly included a non-prime implicant in the table, for example, one that covers only don't care terms and should have been discarded. To the introduced chart, we add one final column that represents the cost associated with selecting each prime implicant. As we discussed earlier, the Quine-McCluskey method supports various cost functions, or figures of merit, to guide the search for the optimal solution as long as the function is additive. This means that the total cost of a solution is computed as the sum of the individual costs of the selected prime implicants. As already commented, in this course, we consider two figures of merit, the cardinality and the number of literals. If the cardinality is used as the cost metric, we assign a cost of 1 to each prime implicant, regardless of its complexity. If we choose to use the number of literals, each prime implicant is assigned a cost equal to the number of literals it contains. Finally, when the cardinality is used, all rows in the table will, by definition, have the same cost. Therefore, the cost column can be omitted without loss of information. Let's look at the considered example. In the first case, where the cardinality is used, the final column of the table consists entirely of ones, since each prime implicant has the same cost. In the second case, where the number of literals is used, you'll notice that each prime implicant has a cost of 2, because, as shown in the previous slide, in this specific example, each implicant is composed of 2 literals. Identifying the cover that minimizes the total cost of the solution is, in general, a computationally intractable problem. More precisely, it is known to be NP complete. Nevertheless, we can exploit certain relationships between prime implicants and minterms to simplify the prime implicant chart before attempting an exhaustive search. In particular, we make use of the essentiality criterion. This is a selection rule that identifies essential prime implicants, implicants that are required in any valid cover because they are the only ones that cover specific minterms. Once such an implicant is selected, we can remove all the minterms it covers from the table, thus reducing the problem size. We also apply the so-called dominance criteria, which help further simplify the table by identifying unnecessary implicants or minterms that can be safely discarded without affecting the optimal solution. There are 2 types of dominance criteria. Row dominance allows us to eliminate redundant prime implicants, that is, implicants whose coverage is fully contained within that of others. Note that whether an implicant is considered dominant may also depend on the cost function in use. Column dominance allows us to eliminate certain minterms that do not influence the outcome of the optimal cover, The overall solution strategy consists of applying these simplification rules iteratively until either an optimal cover is found or no further simplifications are possible. In the latter case, we must proceed with an exhaustive search to complete the covering process. According to the essentiality criterion, if a column in the table contains exactly one X, then the prime implicant corresponding to that X is essential. In this case, we must select that implicant and add it to the cover set. Once an essential prime implicant is selected, we can remove the row corresponding to that implicant from the table and remove all columns for which that row contains an X, since those columns represent minterms covered by the selected implicant. Note that removing columns may cause some rows to become entirely empty. These rows can also be removed since the corresponding implicants no longer cover any minterms and therefore cannot contribute to the final solution. Let's continue with the same example, using cardinality as the cost function. As discussed earlier, we do not need to display the cost column since all costs are equal. In column 6, there is only one X, which corresponds to implicant P4. Therefore, we select P4, remove its row, and also eliminate the columns corresponding to minterms 6 and 7. This brings us to the updated table shown here. As you can see, no further rows need to be removed in this step. Each remaining row still contains at least one X. According to the row dominance criterion, a prime implicant Pi dominates another prime implicant Pj if Pi covers at least all the minterms covered by Pj, and the cost of Pi is less than or equal to the cost of Pj. What does this mean in practice? When the costs are equal, as is always the case when using cardinality as the cost function, Pi is clearly the better choice, since it covers more minterms. If we were to select Pj, we would still need to select additional implicants to cover the extra minterms that Pi covers, but Pj does not. If the two implicants have different costs, as happens when using the number of literals as the cost function, then the decision becomes more nuanced. Pi is only preferable if its cost is less than or equal to the cost of Pj. Otherwise, it might be more efficient to choose Pj along with another implicant Pk, such that, together, Pj and Pk cover all the minterms covered by Pi, and the combined cost of Pj and Pk is less than the cost of Pi. The row dominance rule simplifies the covering table by allowing us to remove dominated rows. They correspond to implicants that are not needed to construct an optimal cover. Let's continue with the previous example. P0 covers minterms 0, 1, and 8. P1 covers only 0 and 1. Since P0 and P1 have equal cost, P1 is dominated by P0 and can be eliminated from the table. This leads us to the updated table shown here. As you can see, we have simplified the table, but we have not made any actual selections yet, so the current cover set remains unchanged. The elimination of a dominated row often leads to a new version of the covering table, in which some columns contain only a single X. Formally, this simplification results in the identification of what are called secondary essential prime implicants. In the current example, we observe that P0 has now become a secondary essential prime implicant for minterm 0. Therefore, we select P0 and add it to the cover set. Next, we remove the corresponding row, P0, and eliminate the columns for all minterms covered by it. Here you can see the updated covering table and the revised cover set. The second dominance criterion applies to columns. A minterm Mi dominates another minterm Mj. If every prime implicant that covers Mi also covers Mj. In other words, Mj is covered by all the implicants that cover Mi and possibly by some additional ones as well. For this reason, we can eliminate Mj from the table, since any choice made to cover Mi will automatically cover Mj as well, but the reverse is not necessarily true. Let's return to the previous example, this time ignoring the simplifications made using the row dominance criterion so that we have a complete table to demonstrate the concept. Minterm 0 is covered by P0 and P1. Minterm 1 is covered by P0, P1, and P2. This means that any decision we make to cover minterm 0, that means to select P0 or P1, will also cover minterm 1. On the contrary, if we were to choose P2 to cover minterm 1, we would still be forced to choose either P0 or P1 to cover minterm 0, resulting in a less optimal solution. Therefore, we say that minterm 0 dominates minterm 1. And to simplify the table, we can remove the column corresponding to minterm 1. This leads us to the updated table shown on the right. Note that, as in the previous simplifications, the cover set remains unchanged. The three simplification criteria we have introduced, essentiality, row dominance, and column dominance, are applied iteratively as long as they can be used. At the end of this process, we may reach one of two possible outcomes: a completely empty table, which means that the final cover has been successfully determined, or a non-reducible table, referred to as a cyclic table. In this case, we must apply pseudo-exhaustive search algorithms, such as branch and bound, which we will study in the next video. Let us now wrap up the considered example. We applied the row dominance criterion. We identified a secondary essential prime implicant, and we reached an empty table. At this point, we can write down the final expression representing the optimal solution and compute its associated cost. We summarize here the algorithm for the prime implicant selection phase. The process starts with step 1, where we construct the prime implicant chart. This table shows which prime implicants cover which minterms. In step 2, we apply the essentiality criterion. If a minterm is covered by only one prime implicant, that implicant is essential and must be included in the final solution. Next, in step 3, we use the row dominance criterion. If one row covers all the minterms that another row does without a higher cost, then the dominated row can be eliminated. Similarly, step 4 applies the column dominance criterion. If one column is covered by all the same implicants as another column, the dominated column can be removed. After applying these three criteria, we reach step 5, where we check, did the table change? If yes, we repeat the process from step 2. If not, we move on to step 6. In step 6, we check whether the table is now empty. If it is, the process ends. This means we have fully covered all minterms. If not, we proceed to step 7. Finally, step 7 involves using a search algorithm, such as branch and bound, to select a minimal set of remaining prime implicants that cover the remaining uncovered minterms. This final step ensures the identification of a complete solution.